Welcome to Module 2, Data Preparation and Property Modeling. In this module, we'll focus on the critical first step of any successful property model, gathering and preparing data. We'll explore how to ensure your data is accurate, organized, and ready to be used for building precise geological models. By setting a strong foundation, you'll improve the reliability of your models and create better results for analyzing and predicting reservoir properties. Let's dive in and get started with data preparation. In Petrel, the integration of facies logs, petrophysical logs, and secondary data is essential for building accurate reservoir models that guide decision-making in exploration and production. Facies logs, including lithology, rock types, and sedimentological facies, provide a detailed understanding of the depositional environment and rock characteristics. By adding data such as biostratigraphy, grain size distribution, and sedimentary structures, users can better interpret the geological history and variability within the reservoir. Petrophysical logs and core data offer crucial insights into the physical properties of the reservoir rocks, helping identify key characteristics like porosity, permeability, and water saturation. Incorporating advanced petrophysical measurements like sonic logs, NMR logs, and capillary pressure curves further refines the model's accuracy. This data is essential for evaluating reservoir quality, estimating reserves, and optimizing production plans. Secondary data, such as seismic attributes and geomechanical information, provides context for well data, linking it to seismic interpretations. Seismic data helps map the spatial distribution of facies and petrophysical properties, while geomechanical data is crucial for understanding rock stability and fluid flow, ensuring safe drilling and efficient production. Using Petrel to integrate these data sets enables geoscientists and engineers to develop comprehensive 3D reservoir models. These models enhance the accuracy of hydrocarbon volume estimations and inform key decisions like well placement and field development strategies. Petrel allows users to visualize, analyze, and predict reservoir behavior, making it a powerful tool for maximizing performance and ensuring sustainable operations. This image illustrates the integration of well log data and cross-plot analysis for reservoir characterization. On the left, the well log panel displays different types of well logs, such as gamma ray GR, porosity PHI, and permeability perm. These logs help in understanding the subsurface properties by analyzing the recorded data. In the middle, a cross-plot between porosity PHI and permeability perm is shown, color-coded by gamma ray GR values. This crossplot is essential for identifying relationships between rock properties, such as how porosity impacts permeability in different lithologies or facies, indicated by the gamma ray colors. On the right, the well log curve and facies interpretation allow for a visual correlation of the logs with subsurface facies, aiding in the distinction between shale and sand layers. This comprehensive approach is useful for identifying reservoir quality and potential productive zones within the well. This module in Petrel is a tool used for well log analysis and machine learning models. The left side allows for log calculations and interpretation, where users can create discrete logs, apply mathematical functions, and set parameters like gamma ray values to identify lithofacies. On the right, the Train Estimation Model panel is used for creating neural network models, allowing users to classify or estimate data from well logs by selecting input variables and training the model for predictive tasks. It streamlines complex analysis for better reservoir understanding. This module in Petrel is a tool used for well log analysis and machine learning models. The left side allows for log calculations and interpretation, where users can create discrete logs, apply mathematical functions, and set parameters like gamma ray values to identify lithofacies. On the right, the Train Estimation Model panel is used for creating neural network models, allowing users to classify or estimate data from well logs by selecting input variables and training the model for predictive tasks. It streamlines complex analysis for better reservoir understanding. To create a facies template in Petrel, follow these steps. 1. Open the Templates pane, expand Discrete Color Tables, and right-click the folder. Select Insert New Discrete Color Table. 2. Open the newly created template, e.g., Untitled one, and click the Remove Rows/Add Rows icon to adjust the number of rows. 3. In the Colors tab, input the facies names and assign colors and patterns for each. 4. Switch to the Info tab and rename the template for better identification. This process helps organize geological facies effectively. To create a property template in Petrel, follow these steps. In the Templates pane, locate and expand the Discrete Property Template folder. Right-click and select Insert New Property Template. Open the newly created template, named Untitled 1 by default. In the default color table list, click More to access additional options. Select the color table you previously created for your property. This ensures your facies or lithology data are appropriately color-coded and categorized for interpretation in Petrel. Creating and interpreting a new discrete log in stratigraphy. 1. Start a new discrete log. Open the stratigraphy module in your software. Click on New Discrete Log to begin a new interpretation project. 2. Select a discrete template. A window with various templates will appear. Choose the discrete template that best fits your interpretation needs. Paint the discrete log. Go to the Well Correlation tool palette. 3. Click on Paint Discrete Log to start adding data to your log. Select a facies code. In the empty track of the log, right-click. 4. Select the facies code you want to interpret from the drop-down list. This process will help you create and analyze discrete logs efficiently, facilitating the interpretation of geological data. Here's a concise step-by-step summary for setting up the log analysis. Select the model type. Use classification for discrete logs or estimation for continuous logs. Select data type. Choose well logs. Choose the wells to use, ensuring the logs have common data. Select the logs that will be used as input data. Click Correlation Analysis to view how the selected logs interrelate. This process helps in understanding the relationships and patterns between different well logs. Okay, now let's take a few minutes to understand this module. The module you're looking at is a neural network tool used for geological analysis. Here's a breakdown of the main sections. Neural network configuration. First, let's talk about how to configure our neural network. You can do this in 2 ways: supervised and unsupervised learning. Options to choose the type of learning. Supervised. Example. You have well data that includes features like depth, rock type, and porosity, and you also have a label indicating whether there is oil, yes or no. These labels, yes or no, are what the model learns to predict. Application. Classifying geological formations into known categories, such as sandstone or shale. Unsupervised. Example. You have well data with features like depth, rock type, and porosity, but you don't have labels indicating whether there is oil. The unsupervised model groups the data into clusters based on similarities, without knowing in advance what these clusters represent. Application. Identifying new geological formations or facies without prior labels. Maximum number of iterations. The limit of iterations for training. Example. Suppose you are training a supervised model to predict the porosity of a geological formation. You start with 20 iterations and observe that the training error keeps decreasing. You increase the number of iterations to 50 and notice that the error no longer improves significantly after 30 iterations. So, you decide that 30 is the optimal number of iterations for your model. Cross-validation, a technique to evaluate the accuracy of the model. Example. You have a data set of 100 wells. You divide this data into 5 equal parts. You train the model with 4 parts and test it with the remaining part. You repeat this process 5 times, each time using a different part for testing. This gives you a good estimate of how the model will perform with new data. Error limit threshold, a parameter to define the acceptable error limit. Example. You are training a model to predict the water saturation in a formation. You set an error limit threshold of 0.01. If the model's error falls below 0.01, before reaching the maximum number of iterations, the training stops. This ensures that you don't spend unnecessary time on additional iterations that don't significantly improve the model. This Petrel module uses neural networks to classify well logs into different facies or lithologies. Here's a summary of the workflow. Model selection. Choose an existing neural network model or create a new one to classify discrete well log data. Output probabilities. Enable the option to output probabilities, allowing you to see how likely a data point is to belong to a specific facies, e.g., class 1 equals sand, class 2 equals clay. Input interface. Select the well logs you want to use as input data for the analysis. These logs are processed by the neural network model to determine the lithology class. Class probabilities. The system generates a probability for each facies instead of rigid classification, providing a more detailed analysis and better understanding of transitions between different sediment types. In summary, this Petrel module allows lithology classification using neural networks, outputting probabilities for each facies instead of categorical decisions, improving precision and well log interpretation. How to use the module in Petrel to create new facies, logs, using the well log calculator. Selecting log variables. First, in the left panel of Petrel, select the log variables you will use in your calculation. These variables can include depth, GR gamma ray, pHI porosity, among others. Calculation formula. At the top of the screen, you will find a box where you can define a formula to assign facies based on data conditions. For example, you can write something like litho_facies equals if GR 7010. This means that if the gamma ray GR value is less than 70, facies 1 sand will be assigned, and if it is 70 or greater, facies 0 shale/clay will be assigned. Log configuration. To the right of the formula, you can select a log template to define how the facies log will look. For example, you can choose the simple litho template. Additionally, you have access to functions and geometry to enhance the analysis. Log reassignment. Here you can adjust the existing sample and redefine the MD, measured depth, from a well log. This ensures that the values are consistent throughout the well. Results visualization. Once you have executed the formula, you will see the result as a facies log on the right side of the screen. This log will show the variation between different facies along the well depth, with a visual representation indicating the areas of sand and shale/clay. In summary, use the well log calculator to generate facies based on specific conditions. Enter a formula to define facies based on data like gamma ray. Configure how the new log will look using templates. Reassign values according to the well depth. Visualize the results with different facies represented along the well depth. This module is an essential tool for classifying different types of sediments in well logs. Is there any step you would like more details on? How to use the module in Petrel to calculate water saturation, SW, using Archie's equation. Step 1. Selecting log variables. In the left panel of Petrel, select the log variables you will use in your calculation. These variables can include depth, GR gamma ray, pHI porosity, among others. Step 2. Calculation formula. At the top of the screen, define a formula to calculate water saturation. Use Archie's equation. SW equals \frac A_W / left \frac phi caret M /right N. Here, SW is water saturation. R_W is the resistivity of water. R_T is the true resistivity of the formation. \phi is porosity, and A, M, and N are constants. Step 3. Log configuration. To the right of the formula, select a log template to define how the water saturation log will look. Access functions and geometry to enhance the analysis. Step 4. Log reassignment. Adjust the existing sample and redefine the MD, measured depth, from a well log. This ensures consistency of values throughout the well. Step 5. Results visualization. Execute the formula. The result will appear as a water saturation log on the right side of the screen. This log shows a variation of water saturation along the well depth with a clear visual representation. Example practical application. Graphical visualization. The screen displays a graphical representation of the data. Shaded or colored areas indicate different levels of water saturation. For example, high water saturation zones might be shown in blue, while low saturation zones might be in red. Data analysis. Use Petrel's tools to further analyze the data. Apply filters, adjust parameters, and compare with other logs for a detailed understanding of the reservoir behavior. Conclusion. Module importance. This Petrel module is a powerful tool for geoscientists and petroleum engineers. It allows precise and efficient calculation and visualization of water saturation in well logs, essential for reservoir evaluation. Benefits. Using this module improves the accuracy of reservoir assessments, optimizes production, and reduces exploration and exploitation risks. How to calculate a fraction of the potential reservoir as a ratio of the total volume. Step 1. Gross thickness calculation. Gross thickness is the total interval thickness. For example, if the interval is from 2,345 meters to 2,252 meters, the gross thickness is 2,345 minus 2,252 is equal to 93. Step 2. Net thickness calculation. Net thickness is the total thickness of sand within the interval. For instance, if the total thickness of sand is 72 meters, then net thickness equals 72 meters. Step 3. Net to gross ratio. The net to gross ratio is calculated by dividing the net thickness by the gross thickness. Net to gross equals 72/93 equals 0.774. Step 4. Pore thickness calculation. Pore thickness is calculated by multiplying the net thickness by the porosity. If the porosity is 32%, then a pore thickness is equal to 72 times 0.32 equals 23.04 meters. Step 5. Hydrocarbon pore thickness calculation. Hydrocarbon pore thickness is calculated by multiplying the pore thickness by 1 SW, where SW is the water saturation. If SW is 0.18, then hydrocarbon pore thickness equals 23.04x, 1 to 0.18, equals 18.432 meters. Example practical application. Graphical visualization. The diagram shows different layers of earth materials and their properties. The calculations help in understanding the reservoir's capacity by showing the fraction of the potential reservoir as a ratio of the total volume. Data analysis. These calculations are crucial for evaluating the reservoir's potential and making informed decisions in petroleum engineering. Conclusion. Importance of calculations. These steps are essential for accurately assessing the potential of a reservoir. By understanding the gross thickness, net to gross ratio, pore thickness, and hydrocarbon pore thickness, we can make better decisions in reservoir management. Benefits. Accurate calculations lead to better reservoir evaluations, optimized production, and reduced risks in exploration and exploitation. This Petrel module is used to calculate the net to gross (NTG) ratio for a well, based on key well log parameters. Here's a brief explanation. Select variables like VSH shale volume, PHI_temp porosity, and SW_RG water saturation from the well logs. The formula calculates NTG using conditions: VSH less than or equal to 0.45. PHI_temp greater than or equal to 0.15, SW_RG less than or equal to 0.8. If all conditions are met, the NTG value is 1 net. Otherwise, it's 0. You can attach the calculation to a log template and use additional functions for fine-tuning. The output is displayed as a new well log, showing net and non-net zones based on the conditions. Additional configuration allows you to generate logs or adjust properties based on the NTG calculation. In summary, this module efficiently calculates and visualizes net to gross, helping to identify productive zones in the subsurface. After 21 intense minutes of learning and practice, you've now reached a point where you have the capability to complete the exercises with confidence. The foundational tools of Petrel, understanding how to calculate net to gross, using neural networks for classification, and analyzing well logs are all within your grasp. You've seen how formulas are integrated into the system and how data is visualized to interpret subsurface geology. Now, you're fully equipped to take on the next set of tasks, where you'll apply these skills seamlessly, building on the knowledge gained from each previous step. What once seemed complex is now clear, and you're ready to put it all into action. Thank you for your perseverance and focus during this learning journey. You're more than ready. Go ahead and tackle those exercises.